So in the last class, we have discussed about the oil circuit breakers and air circuit breakers. So in this session, you are going to discuss about the vacuum circuit breakers, which are oilless circuit breakers. So vacuum circuit breakers phenomena is different from oil and air brake circuit breakers as well as SF6. We should know what is vacuum, how it is acting as a medium for arc quenching. So these are the various pictures of the vacuum circuit breakers you can see. So this is a picture in the substation, and this is the way the mechanism existing. So this is the vacuum circuit breaker. That's where we are going to discuss how it operates. So this is a 36 kV porcelain enclosed 3-phase vacuum circuit breaker picture. So we can see in one interrupter how the operation takes place. Here the fixed and moving contacts, how they are, you can see here. This is one way of mechanism. So this is the just an outlook how the vacuum circuit breaker appears. So before going to discuss about the vacuum breaker operation, first we will see the principal used in the vacuum breakers. You see, when two current carrying contacts are separated in a vacuum module, that means low pressure, vacuum is low pressure, an arc is drawn between them. That arc, when it is drawn, an intensely hot spot is created. Hot spot is created at the instant of contact separation. So this hot spot, at this hot spot, metal vapor shoot off. Vapor shoot off. That vapor consisting plasma. This amount of plasma and amount of the vapor liberated is proportional to arc current. What is the amount of the arc current is there? Depends upon that the vapor or plasma will be there. So the rate of vapor emission depends upon the arc current. So normally the current goes through zero. At current zero, that means when the arc current decreasing during the portion of the wave, at this position, the rate of vapor emission tends to zero. For a brief moment, the rate of vapor emission tends to zero. So therefore, plasma tends to zero at this brief moment. Soon after current zero, the remaining metal vapor condenses and the dielectric strength builds up rapidly and the restriking of the arc is prevented. So this is the principle behind a vacuum circuit breaker. So how it works, let us see. So vacuum system is one in which pressure is maintained at very low value, below the atmospheric pressure. We know what is atmospheric pressure? At 0 degrees centigrade, 760 mm of mercury is 1 atmospheric pressure. 1 mm of Hg pressure is also known as 1 torr. That is the name given after Torricelli, who is the first to obtain the pressures, the alpha of mercury barometer. So that is 1 torr. That means 1 mm of Hg. You see, 760 mm of Hg at 0 degrees centigrade is 1 atmospheric pressure. We are talking about 1 mm of Hg. That is 1 torr, 10 power minus 3 torr. That is called micron. You see, 1000 times below. 10 power minus 3 torr is known as 1 micron. It is possible to obtain the pressures as low as 10 power minus 8 torr. That means torr means 1 mm of Hg, 10 power minus 8 torr. Such a low pressures can be obtained. This is called vacuum. Vacuum means where the mobility can be restricted. You see here one picture. Here the breakdown voltage versus absolute pressure if you take. So vacuum level is expressed in terms of torr, as I said. The breakdown voltage of certain gap varies with absolute pressures. Okay. So as the absolute pressure is reduced from 10 power minus 1 to 10 power minus 3, as the pressure is reduced, as pressure is reduced, then what happens? Dielectric strength builds up. Dielectric strength means which is deionization force. when the dielectric strength builds up, then what happens automatically? The arc won't restrike again. So as the pressure decreases, dielectric strength builds up. About 10 power minus 4 torr, at about 10 power minus 4 torr, if you see, the characteristic is almost flat. And the dielectric strength in this region is about 12 kV. Peak per mm. Per mm, 12 kV is the dielectric strength. So the vacuum interrupter in a vacuum level of the order of 10 power minus 6 to 10 power minus 10 also. That means very, very low pressures can be possible. This is called high vacuum range. So during the passes of time, what happens? After the arc interruptions, vacuum level goes on reducing. However, it remains in the range of 10 power minus 8 to 10 power 5, minus 5 to 10 power minus 8. Vacuum in the range of minus 3 to minus 4 is sufficient for the interruption and withstanding of impulse test voltage. That means this vacuum is enough for the interruption, but even we are maintaining the vacuum at below low value also. So this is about the dielectric strength versus pressures. So these are the various examples: vacuum interrupter 3.6, 7.2, 12, 35 for indoor metal clad, 1.2, 3.6, 7.2 kV for indoor metal enclosed control gear, and vacuum interrupter rated this range 3.6, 7.36 kV for outdoor porcelain housed multi interrupters. If the voltage is very high, 72.5 kV and above, as I said, when the voltage increases, we need more interrupters to be connected in series. Single phase 25 kV, 25 kiloampere circuit breakers have two interrupters for railway track side applications for 25 kV single phase substations. So as I said, 10 power minus 3 is 1 micron to 10 power minus 8 mm of Hg. So this is the pressure can be maintained low pressure for a gap of, you observe, 0.3 to 0.5 mm of Hg. You see, it is not even mm, 0.3 mm. Even you cannot imagine how much opening is there between the contacts. So vacuum circuit breakers, they are unique, small contact travel, less weight, because we are not maintaining any air at high pressure or oil you are not maintaining. It is just a vacuum, that means low pressure. So less weight of moving parts, long life for given rated current. So SF6, if you take it, is unique, high read, heat transfer capability, fast decompression. We are going to discuss about SF6 after vacuum circuit breakers. So vacuum circuit breakers, normally if you take discharge in the gas, if there is a discharge in the gas, there is a small mean free path. Mean free path means the path available for the movement of the electrons. So if the mean free path is more, then there is no possibility of the collision of these electrons. One electron cannot collide with another molecule and it cannot produce other electrons. That means avalanche breakdown is not possible. If the mean free path is less, there is a possibility of collision of these electrons with molecules and another electrons will be formed. Like this, the repeated bombardment, it will produce more electrons, which is called avalanche breakdown. That generally happens in normal gas. In the normal air, that will happen. If you take the vacuum, it has the mean free path of few meters. You may observe, sir, only 0.3 mm, 0.5 mm opening is there between the contacts. How can you say in meters? Yes, in terms of electrons, the movement, if you observe, it is in terms of meters you can see, because they cannot collide with other molecule and no electron can be generated. That is in terms of electrons movement, it is in terms of meters you can say, because vacuum does not allow this electron movement. So that is the difference between discharge in gas and discharge in vacuum. Therefore, the current growth prior to breakdown cannot take place due to formation of electron avalanche. So, however, it would be possible to liberate gas. Here, one point you have to understand: the vacuum also, there is gas production in the vacuum by some means. What is that? You will see the discharge would take place according to Townsend process. Vacuum arc is different from general class of low and high pressure arcs, what I have discussed previously. So the pressures below 10 power minus 5 mm of mercury are considered to be high vacuum. Charged particles from one electrode moving towards other electrode at such a pressure are unlikely to cause the collision with the residual gas molecules. They cannot collide each other. and that means the electron cannot collide with other gas molecules between them. So hence ionization by collision of particles with atoms and molecules is less. Ionization means arc means ionization. That ionization process is very less in vacuum relative to that of the gas. So keeping very small gap between the electrodes in the vacuum, if the voltage is gradually increased as certain voltages, the gap breaks down suddenly and current increases suddenly. This phenomenon is called vacuum breakdown or vacuum spark. Generally, in the vacuum, how test can be conducted? Keeping small gap, increase the voltage between the gap, and if a small some breakdown occurs, that means there is some flow of electrons between that. That is called vacuum spark. Pressure remaining constant. Nature of characteristics depends upon the surface condition, material of the electrodes. Here, in this circuit breakers, we are going to discuss about the type of material used, the electrodes, the type of the material used for the electrodes. This point we are going to discuss very clearly because it is a vacuum. It is not air or it is not oil. There is no special medium. It is a simple low pressure vacuum. Then we are going to focus on electrodes, type of electrodes. So discharge, that's what we are going to discuss about the electrodes metal. So vacuum arc, if you take electrons, ions, and neutral atoms, they come from electrodes, not from the medium. This is very important. Medium is generally, if you take oil, hydrogen gas is liberated. If you take air, it has its own nature of punching the arc. But it is a vacuum. There is no possibility of the production of electrons from the vacuum. But these are coming from not coming from medium. These are coming from whatever the material you are using for the electrodes. Okay. So because of the large mean free path, as I said, for electrons, the electric strength of the vacuum is 1000 times more than the gas due to large mean free path. Okay. So the breakdown strength depends upon condition of the electrode, gap length, but not based on the gas density. Okay. Here it is a vacuum. Mainly the breakdown strength, gap breakdown strength depends upon the electrode condition and gap length. So highly here one more thing you have to understand. As I am saying, the material you are using, if the contact is very smooth, highly polished contact is there, then it has high breakdown strength. Okay, highly polished and thoroughly degraded electrodes have show higher breakdown strength. But generally what happens due to repeated operations, contacts get roughened. Then what happens? The breakdown strength decreases. So that means on the contact there will be some deposits. Deposits will be there. Then the contacts will be roughened. Because of that breakdown strength decreases. Then how to remove these small deposits on this? Simply by using successive high voltage impulses. So dielectric strength improves by applying successive high voltage impulses, which removes loosely adhesive metal parts on that. This is a way the breakdown strength can be improved. Here, if you see, so these electrodes, as I am saying, they are very important. Mostly they are made by silver, bismuth, copper. At 10 power minus 6 star, more breakdown strength for gap less than 3 mm. So that means here we are discussing about the gap length as well as the type of electrode you are using. So it has been observed that for vacuum of 10 power minus 6 star, some of the metals, that's what I said, attain their maximum breakdown strength when the gap is 3 mm. This property of the vacuum switches permits the use of short gaps for fast operation. So let us continue our discussion with the vacuum arc. What is the vacuum arc? Generally, discussion will come. How the vacuum arc is different from regular normal high voltage arc. So vacuum arc, as the current carrying contacts are separated, cathode spots are formed. They are called hot spots, depending upon the current to be interrupted. So here you can see for low currents, if the current is low, highly mobile cathode spot. For high currents, multiple number of cathode spots will be created. So these spots constitute the main source of the vapor. This hot spot is the main source of the vapor that is produced in the vacuum circuit breaker. So the process involved in drawing the arc will be due to high electric field between the contacts or resistive heating produced at the point of operation, a combination of both. Because of this, the vapor produced. So the temperature of the hot spot is 6,000 to 15,000 Kelvin. So such a high temperature you can observe. So the cathode surfaces normally are not perfectly smooth, but they have many micro projections. That means we can see small projections on the cathode. When the contacts are separating, the current flowing in the circuit will be concentrated on these micro projections, as we discussed in the previous slide. Micro projections as they form the last point of contact. When they are separating, when the contacts are just like when they are separating at the micro, that means at these projections, more current is concentrated on that spot. So due to their small area of cross section, the micro projections will suffer from explosive evaporation. Those projections, and as I said, when they are separating like this, at this point of contact, there are micro projections in that they suffer excessive evaporation by resistive heating and supply sufficient quantity of the vapor. That is the way the vapor is produced in the vacuum circuit breakers. So in case of vacuum breakers, emission occurs only at the cathode spot, not from the entire surface of the cathode. So entire surface normally is very smooth. So only when you take the cathode, what are the small micro projections are there? There only there is more current concentration in less area, therefore more vapor will shoot up. So vacuum arc is also known as cold cathode arc. So okay, so this emission of electrons are due to different effects: field emission, thermionic emission, field and thermionic emission, secondary emission by positive ion bombardment, secondary emission by photons, pinch effect. These are the various reasons for emission of electrons. Okay. So this is what we have discussed, how the electrons emission takes place. So coming to the next important thing is vacuum arc stability. It is very important. Stability of the arc, it plays a vital role in the interruption process. Normally, if you take in AC circuit breaker, current passes through 100 times in a second. So at current 0, what happens? At current 0, the arc momentarily becomes, the arc intensity decreases. So at that current 0, it is desirable to interrupt the current when it is passing through 0 current. Otherwise, what happens? Power voltage will be induced, as we said, restriking voltage due to current chopping. Because when you are discussing about this current 0 point, current chopping, already we have discussed low currents. Chopping may take place with high blasting effect. Current chopping may take place. So for successful arc interruption, it is necessary to be stable for half cycle. So if you want to interrupt the arc, at least it should stable for half cycle. Otherwise, what happens? It leads to current chopping. That's what we have discussed in the current chopping. So that means arc should be stable. That means vacuum arc should be there at least for half cycle. The stability of this vacuum arc depends upon contact material and its vapor pressure. How much vapor pressure is there? What is the type of contact material is based on the stability will be there. And circuit parameters, voltage, current, inductance, capacitance. These circuit parameters also plays important role for stability. You see here one point: high vapor pressure, low temperature. The vacuum arc is stable for half cycle. That means there is a possibility of interruption. Otherwise, it leads to current chopping. So bismuth and zinc, they have this property. Thermal conductivity of the metal affects the current chopping. Because current chopping is an important point. If the current chopping takes place, restriking voltage occurs, therefore arc may restrike again. To avoid the current chopping, this arc must be stable for at least half cycle, and that means until it reaches the natural current 0, the arc should be stable so that interruption can be quick. So good heat conducting metal, if you take, evaporation rate decreases, arc will be chopped due to insufficient vapor. If you take good heat conducting material, then what happens? Evaporation rate decreases, chopping occurs. If you take bad heat conductor, it maintains temperature. If you take wood, what happens? It is a bad heat conductor, therefore you can see the smoke for more time. Like that, if it is a bad heat conductor, it maintains temperature, longer vaporization, and arc is stable. That means it is not subjected to current chopping. So these are the things we have to discuss when you are talking about the stability. So besides the vapor pressure, thermal conductivity of the material also affects the current chopping level. So these points already have discussed. Okay, based on this, which type of metal or material to be selected will be there. So here a shunt capacitor connected across the breaker contacts reduces the average lifetime of the arc. Higher the value of the capacitors, more is the reduction in the lifetime. We want the arc to be stable at least for half cycle. For that, we can connect a capacitor in parallel to the contacts. An inductance in series, on the other hand, increases the lifetime of the arc. Similarly, higher the system voltage, arc is this for longer time. So current chopping. This is what we have discussed repeatedly. Current chopping in air and oil circuit breaker due to instability in the arc curve. In an air blast circuit breaker, we have discussed low current with high blasting effect. The current is chopped. That chopping is different. In vacuum circuit breaker, the current chopping is different. So you will get questions on this current chopping in the vacuum circuit breaker. What is the vacuum arc? These type of different questions you can get in the vacuum breakers. So current chopping in air and oil circuit breakers occur due to instability of the arc column, whereas the vacuum breakers, it depends upon the vapor pressure and electron emission properties of the contact material. It is possible to reduce the current level at which chopping takes place by placing contact material which gives sufficient metal vapor. We want sufficient metal vapor which stays for at least half cycle to allow the current to come to a very low value, but it is normally not done as it affects the dielectric adversely. Okay, so here to limit current chopping, proper selection of the contact material is required. High vapor pressure, low conductivity metal for current chopping. It is used for current chopping because high vapor pressure, low conductivity means the arc is stable for some time. Low vapor pressure, it is for arc extension. That means if you want to extend the arc, vapor pressure must be less. If you want to avoid the current chopping, high vapor pressure is required. If you want both the advantages, no current chopping and extension must be fast. If you want both the things, you need a combination of these metals. So high boiling point, okay, have low vapor pressure at high temperature, but poor conductivity. So low boiling and melting point has high vapor pressure at high temperature, good thermal and electrical conductivity. So boiling melting points, these are required for current chopping and arc extension. That's why we'll use combination of these metals: copper bismuth, copper lead, silver bismuth, silver lead. These alloys will be used for the electrodes manufacturing. So that is required for current chopping and arc extension. So therefore, to combine these conductivity properties in one single material, composites of two or more metals or metal or non-metal have to be made. So that's what we said. This is the combination which are alloys to be used for contact materials. So vacuum arc recovery phenomena. The recovery phenomena means what? The cooling. When arc interruption is over, then what happens? Space between the surrounding electrodes is filled with vapor and plasma. So once the interruption is over, immediately what happens? It is completely filled with vapor and plasma. So presence of this residue affects very much the ability of the interrupter to withstand high voltages. So these residues must be cleared as quick as possible. The process by which this residue decays, by which vacuum gap regains its dielectricity, is known as arc recovery phenomenon. As quick as possible, these residues must be cleared. Okay, so at current zero, the cathode spot extinguishes within 10⁻⁸ seconds. You see, cathode spot, which is the main source for this arc, that will extinguish in 10⁻⁸ seconds. After this, original dielectric strength is established very soon. So that's what it is. So condensing, quick diffusion of the metal vapor to glass walls, these are important. So for building up of the dielectric strength after current zero, because at current zero arc is interrupted. After current zero, we have to build up the dielectric strength quickly so that arc is extinguished quickly. So for that, these two factors are important. So if you take the vacuum circuit breakers, the recovery strength is 1 kilovolts per microsecond. That means for every 1 microsecond, 1 kilovolt. What is the meaning of this? You see, 133 kV system is there. Suddenly short circuit occurred. Suddenly this 33 kV becomes zero. That means voltage is zero. Once the breaker opened and the arc is cleared, it will be closed. Again, you have to get back the 33 kV as quick as possible. So that is called recovery. That is called recovery. Here with vacuum, for 1 microsecond, you will get 31 kilovolts. For 33 kV to recover back, you will get 33 microseconds. You see, that is such a fast way you will get back the voltage. So for arc current of 100 amperes, this is vacuum circuit breakers. Whereas if you take the normal air gap for 1 microsecond, 50 volts only. You can observe the difference. Here for 1 microsecond, 1 kilovolt, we can get back the voltage. For air gap, it is only 50 volts. Such a fast recovery can be obtained with vacuum circuit breakers. So this is the construction of the vacuum breaker. Here you can see various parts here. This is the fixed contact. This is the end cap. You can observe a jar, a glass jar, which has a that means a metal cap on the glass jar. You can see through is there, and you can see what is happening inside the jar. So this is a jar. You can see a ceramic envelope where end cap is there, here and here caps are there, and these are fixed contact. Fixed contact and end cap, they are connected together. That means if you open along with fixed contact and end cap, both will open. And this is a ceramic envelope for examination purpose. This is the contact. These are the contacts, the separation. This is the sputter shield, and these are the bellows through which the movement will be there. That means moving contact will move down to this. Okay, let us see. The outer envelope is normally made of, this envelope is made of glass. Why it is made of glass? Due to ease of joining it to the metallic end caps, and also because the gas envelope makes it easy to examine from the outside the state of contacts after the breaker is interrupted, the current. When the breaker is interrupted, what is the state? So what is the examination? The change from silvery mirror-like finish to milky white color shows Buffel is losing its vacuum. So this change of color is an examination that there is a opening of the opening of these contacts, and there is a formation of the vapor inside, and action is taking place. The sputter shield, if you see, this is the sputter shield, which is this is outer envelope. This is the sputter shield. Is provided between contacts and outer envelope in order to prevent the metal vapor reaching the envelope. The metal vapor reaching the envelope, it should be avoided as it reduces the breakdown strength between the contacts. This vapor, what is formed inside this, that should not reach this envelope. For that case, a sputter shield is provided here between the contacts. This is generally made up of stainless steel. Inside the sputter shield, the breaker has two contacts, one fixed contact, another moving contact, which moves through a distance of 5 to 10 mm, very small gap length. So depending upon the operating voltage. So depending upon the operating voltage, either 5 mm or 5 to 10 mm, that variation will be there. So the metallic bellows here, bellows means they are a moving mechanism to move it downwards. Is made up of stainless steel. It is used to move the lower contact. So the design of these bellows is very important as it decides the life of the circuit breaker. The life of the circuit breaker, and also the ability of this part to perform repeated operations, because it has to move like this. Repeated operations, number of operations to take place depends upon these bellows only. The movement will be properly, the closing and opening movement will be there. The life of the breaker depends upon these bellows. Okay. So you can observe this circuit breaker in different way here like this. As I said, these contacts, fixed and moving contacts, you can see this is the cylindrical shape like this. Okay, this is cylindrical shape. This is the moving contact which is connected to these belows. You can see these are the belows, which makes the moving contact to move like this. This is fixed contact. It is a cylindrical shape. Till now, I have discussed about this material of this contact. So normally, this very smooth material, cylindrical material, any micro projections are there. Those micro projections are the cause for metal vapor. So it is a cross-sectional view of that below spotter shield, and this is outer envelope. This is the spotter shield. These are the belows, and all the things. What is we have seen here. Generally, you have to draw this picture in the examination. The periphery of end cap is sealed to envelope. This is the one, and fixed contact stem. This is fixed. These two, these fixed contacts is integral part of this. This means if you take some cap, something is kept on that. This is the fixed contact. This is the cap. So if you open the cap, this fixed contact also open along with that. So that is integral part. One end cap sealed to envelope, and fixed contact stem is integral part of the one end cap. One end of the fixed as well as moving contact is brought out of the chamber. So here we are taking fixed contact and moving contact brought out of the chamber for external connections. The lower end of the bracket is fixed to spring operated. This is the one I said, solenoid operation. So the spring solenoid operation or spring operation will be there, so that the metallic belows inside the chamber are moved downward like this. They move downward and upward, downward upward movement during opening and closing operation respectively. It is to be noted that the operating mechanism should provide sufficient pressure for a good connection between the contacts. It should avoid bouncing action. At the instant, whenever you want, it should close, it should open. Opening, closing must be proper. There should not be any bouncing action. That's why the life of the bracket depends upon this mechanism. So here, another way we can see the construction of this interrupter. I have said enclosure, end flanges, contacts. So these are another way you can give a detailed explanation. So as I said, 10 power minus 8 torr is the vacuum can be maintained. So this is other way to view this circuit breakers. So these are two basic forms of interrupters suitable for single unit per pole, multi unit per pole. Okay, you go through this text, which is same as the previous one. So vapor condensing shields and metallic belows, that's what we discussed. And seals, sealing techniques are similar to those used by electric valve and power tube manufacture. These are like metal glass, metal ceramic seals. These are the sealings like this. So here, the important is the moving contact is connected to the operating mechanism by means of glass fiber rod. Vacuum interrupters are being increasingly used in metal clad switchgear of voltage 3.6 to 15 kilovolts. Generally 3.3 to 13 kilovolts, 33 kilovolts like that we'll say. Sometimes 3.6 to 15 kilovolts range we can say. So what are the merits of the vacuum breakers? They are self-contained and does not need filling of gas or oil. They do not need auxiliary air system, oil, etc. No emission of gases, pollution free, non-explosive, silent operation, modest maintenance of the breaker, non-maintenance of the interrupters, hence economical. Breaker forms a unit which can be installed in any orientation. Breaker is compact and self-contained. Large number of operations on load or short circuit, suitable for repeated operating duty, long life, suitable for capacitor switching, cable switching, industrial load switching, and constant dielectric. There are no gas decomposition products. Just like oil circuit breaker, there is sludge formation. Like that, there is no gas decomposition products in vacuum. Hermetically sealed vacuum interrupter keeps out all environmental effects and constant contact resistance. In vacuum, the contacts cannot oxidize, right? Which ensures that a very small resistance is maintained throughout their life. The very important thing is high total current switched. Since contact piece erosion is small, because erosion is less, rated normal current can be interrupted up to 30,000 times, and rated short circuit breaking current on an average 100 times. So very high current can be interrupted. These reasons, together with the economic advantages offered, have boosted acceptance of these vacuum breakers. So if you see the demerits, vacuum is more expensive than interrupting devices, because maintaining this vacuum so is very important in other types of breakers. That's why its cost is affected by production volume. So it is uneconomical to manufacture small number of vacuum interrupters. We have to produce more number of interrupters. So then only it is economical. Rated voltage of single interrupter is limited above 20 kV. Above 36 kV, two interrupters are required to be connected in series. As I said, when voltage increases, interrupts are connected in series. Vacuum interrupts requires high technology for production. In the event of losses of vacuum due to transit damage or failure, the vacuum is not maintained, entire interrupter rendered useless. For interrupters of the low magnetizing currents in certain range, additional surge suppressors are required in parallel with each phase of the VCD. Sometimes these additional suppressors are required. So, yeah. So as I said, these are the, because of various advantages you have taken, they are used in different applications. Low fault interrupting capacity, cost is low, short gap, excellent characteristics, and very important thing is maintenance required is less. In India, country like in India, where very big complex of rural electrification program is there, the distribution network is mostly 11 kV to 33 kV. There, these breakers are more suitable, and they give fast triple RV applications for fast triple RV. Where voltages are high, current to be interrupted is low. These breakers are